Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 3 from Chapter 2 on an Introduction to Multiple Linear Regression. So we'll jump down to the timetable from the table of contents, and we'll scroll down to Class 3. There is an R Markdown file here and a data file. I'm starting to download the files starting at this video, so I'm going to grab this ADA functions. If you haven't already done that, please do that. And I created a folder on my desktop. I recommend that you find a better place than your desktop to store your own information, but this is sort of just a temporary place for me to put the course materials for these videos. So I'm going to save that file up there. I'm also going to save the Markdown file and the data file to that same location. So save link as to that ADA2 folder, same thing with the data. And when I compile the Markdown file, I should get the HTML file. So I'm going to open the HTML file in a new tab. I just held down Control and clicked on HTML, and it opened the new tab window over here. This is exactly what we should see when we run this or knit this file. I'm going to open up our studio, and I've done nothing but open the file here. I'm going to go to the folder, my desktop, ADA2, and open the Markdown file. Okay, so that puts the Markdown file in this editor window in the top left corner. And I should be able to knit this now. Now, while that's knitting, I'm going to do a couple other things. One is I'm going to set the working directory to the source file location. And that way, in my console window, now when I look for files, it'll look in the right place to find those files. Okay, so the knitting process finished, and I got this document. I always like to look at it in the browser instead of in this RStudio browser. And these two files are exactly the same. So the knitting process worked. Let me take you through the assignment. So we're looking at fitting a multiple regression to understand how the selling price of grandfather clocks depends on the age of the clock and how many bidders there are at an auction. And that's what this says here. There's 32 clocks. This was conducted in England, so we're looking at pound sterling. And we start by loading in the tidyverse. We source that ADA functions.r file because there is a function in there that I wrote to help us create a bunch of diagnostic plots. And we read the data set in. So I think what I'll do is let me just sort of walk through the various parts as a quick overview, and then I'll come back and we'll cover each question in turn. So we start by reading in the data set. We have some summaries here of the variables. Price here is the response variable, and we want to know how price relates to the age and the number of bidders. I start by creating a scatter plot matrix to look at the relationships between variables. And every time you see a solution subsection, that is where you want to answer the question that I ask above. So in this case, let's see, in the scatter plot matrix below, interpret the relationship between each pair of variables and also indicate whether a transformation is suggested. Okay, so down here we would address that request. Okay, then there's a correlation plot. We want to interpret these hypothesis tests for correlations. So in the first, this R core function gives us the correlation values, and then it also gives you p-values for testing whether the correlation is different from 0. So for example, between age and price, the correlation is 0.73, and the p-value for testing whether that correlation is equal to 0 is very small, 0.0000 something. Then we're going to interpret these plots. I basically plotted the data in two different ways, where price is the response variable. We've got age on the x-axis, and just fitting sort of a naively fitting just a regression line between price and age. But I put the third variable, bidders, as a colored. So the darker it is, the fewer bidders, and the lighter, more bidders. So it turns out that there's like dark values down low and light values up high. So it looks like there's a gradient with bidders related to price. And in fact, if you do plot it that way, bidders on the x-axis and price on the y-axis, you also see a positive relationship. And now we've coded the color with age, and as the age of the clock goes up, these are old clocks, they start like at 100 years old and they go up to 200 years old, something like that. We also see this gradient of dark to light. And so I want you to interpret these relationships, sort of similar to what I just discussed. All right, then we're going to fit multiple regression, assess the model assumptions, and if the model assumptions aren't fit, if the assumptions aren't met, then we are going to transform some variables. Okay, so we fit the linear regression here and look at the diagnostic plots. This comes from that ADA functions.r, and we'll look at this more closely later, but all the model assumptions look pretty good. The only one that sort of suggests any issue at all is this Box-Cox plot, where there seems to be a preferred transformation of the response variable of 0, which is a log transformation. But it turns out from the other plots that we can sort of get away with not doing any transformation. So for each of the diagnostic plots that we see above, we should give an interpretation of what we learn from there. Basically, you should be able to look at each plot and know what information you can learn from it and what decisions you would make based on that information. Furthermore, there's some added variable plots to interpret. And those plots were up here, these two here. Then we're going to conduct some hypothesis tests for each coefficient in the model. So after we fit the linear model, we look at these estimates. So these are basically like slopes for, how does, for each increase in age, for each unit increase in age, what is the expected increase in price? So for every year older, we have 12.7 pound increase in the price. And there's a standard error. The t-statistic is the estimate divided by that standard error. And then we have a p-value based on the t-distribution, which uses this number of degrees of freedom down here. And this tells us whether or not what we estimated, whether we believe that it's different from 0 or not. So we're going to write some interpretations there. I'm going to interpret the coefficient of the coefficients of the multiple regression model. So those coefficients are these estimates under this column, the 12 and the 85. Interpret the multiple r² value. That is this value here, not the adjusted, just the multiple r² value. So about 90%. And finally, summarize your findings in one sentence. So, what is your conclusion from all the work that you did? What did you learn? And finally, I do provide some commented code at the very bottom. If you wanted to view the regression model in 3 dimensions, you could uncomment these lines of code, or just sort of highlight the pieces of code after the pound sign and run those, and you would see a 2-dimensional surface in 3 space that you could rotate around. So that's the basic overview. This is a very nice example. There's no tricks. There's nothing weird. The data are basically beautiful and don't need any extra work to make this regression work. All right, so let's dig into the details. We'll go over to RStudio, and I had previously set the working directory so we can, it knows the RStudio knows where to find the data. We'll scroll down a bit, and I'm just going to run each chunk of code that I get to, and then we'll start filling in our answers as we go. Okay, so we'll run this here, and it loads the tidyverse package, and if this worked for you, then you'll get the data set will be read in, and then we can see the structure of the data set and a summary of the numeric values. Whoops. There we go. All right. In the scatter plot matrix below, interpret the relationship between each pair of variables. You know what? I think I'm going to sort of narrate a lot of this stuff. There really is no code to write for this assignment. Almost all of it is just interpreting what we see. So let's just sort of walk through what we see, and as a way to help get you started. So the question here, in the scatterplot matrix below, interpret the relationship between each pair of variables. If a transformation is suggested by the plot, if you had a curved relationship, then indicate that. Then we should also plot the data on the transform scale and perform the following analysis on the transform scale, meaning the multiple regression. So otherwise, just say that there's no transformation necessary. So what are we looking for? We want to know what the relationship is between each predictor variable, age and bidders, on the response variable price. And I have plotted the data in this way, with price as the last variable in this case, and the scatterplot matrix on the bottom, so that price is on the y-axis. Okay, when you have a data set, the response variable may be somewhere in the middle of the variables. My recommendation always is to order the variables in the data set in such a way that you can put the response variable either as the last variable, like this one is, with a scatter plot on the lower diagonal, or put price as the response variable as the first variable and put the scatter plot matrix above. In either of those cases, the response variable will be on the y-axis, on the vertical axis, and then you're sort of looking at the data the way you'd like to, where the predictors take the x-axis. Okay, so what do we see? We see that there's a nice positive relationship between price and age. The correlation in the corresponding position in the upper right-hand corner, where price and age are together, is 0.73. That's quite a strong correlation. Between bidders and price, there also seems to be a bit of a positive relationship, and the correlation value up here confirms that. Between age and bidders, now ideally, between your predictor variables, they are not correlated. But of course, you don't have any control over that. You just sort of hope for that to be true. When there is correlation, that's called multicollinearity. And if that multicollinearity is too large, then it creates problems with hypothesis testing within a regression model. And we'll discuss that later in the semester. But in this case, it looks like there's really no relationship here. The correlation suggests a slight negative correlation. So I don't see any need here for a transformation. We don't really have like a curved relationship between age and price or bidders and price. So all this looks pretty good to me. The things that I just said, I would put down here in the solution. I'd say, fairly strong correlation between age and price, moderate correlation between bidders and price, no correlation between age and bidders, no curved relationships, so no need for transformation. That's how I would summarize what I see there. For the correlation matrix, we're testing whether the correlation between each pair of variables equals 0. So I want you to interpret the hypothesis tests and relate that to what we observed above in the scatter plot matrix. So we should see that there's correlation between age and price, correlation between price and bidders, but no correlation between age and bidders. That's what we're expecting. Let's see if that's what we see. So there's two tables here. The first one are the correlations, and the second one are the p-values for the test. So between age and bidders, we have a negative 0.25 correlation, but a p-value that's less than 0.05. Now, the question is, what threshold should we be using for testing these correlations? We are testing 3 correlations simultaneously. And so if we were using Bonferroni's adjustment, right, we would be looking at, say, 0.05 divided by 3, because that's the number of tests we're performing. So I guess I will suggest that you use this as a threshold for your alpha level threshold for your p-value test. And so I would compare each of these p-values to this threshold. Okay. So it looks like there's not insufficient evidence, right? So you want to write out what the hypothesis test is here, and I guess we can do that together. I don't know, that maybe that's let's avoid getting too much in the weeds. Maybe it's enough to say that, you know, the p-value here is greater than 0.0167, and therefore we have insufficient evidence to conclude that there's correlation between age and bidders. For price, there is sufficient evidence that there's a correlation between age and price. And for bidders and price, now this of course is significant at 0.05 since it's smaller, but it's not smaller than 0.0167. So it looks like there's insufficient evidence here to say that there's a correlation between bidders and price. Part of that is maybe that we've got a smaller sample size. It's also that we evoked the Bonferroni multiple comparison correction to our 0.05 p-value. Anyway, that would be my conclusion, that correlation between age and price, and not quite enough evidence between bidders and price. All right, and that is consistent with what we saw above. We see this weak relationship between bidders and price, but once we correct for multiple comparisons, we don't have the enough power to say that we've got that relationship. So now we've got the plot interpretations. We want to interpret the relationships between all 3 variables simultaneously. Okay, so for example, say how price relates to age, then also how price relates to bidders, conditional on age being a specific value. So just sort of talk that through. How does price relate to age? That's this first plot on the left, right? As age increases, price increases. And then, how does price relate to bidders, conditional on age? Okay, so I mean, when you conditional on age, that means choose an age, right? So let's choose an age of 150, just because it's in the middle. And what is the relationship between price and bidders? Okay, so for 150, as you scroll up, so sort of like look at points that are nearby. Bidders, when bidders is low, meaning dark values, then price is low. And as you increase over bidders, meaning go from dark to light, lighter, then price goes up also. That's for a specific age. Now, of course, I don't know if there's any 2 clocks here that have exactly the same age, so I'm sort of looking within a range. Same thing down here, sort of for clocks that are around 110 years old, sort of this range. We have dark bidders on the bottom, light bidders at the top. So as bidders goes from low to high, price also goes from low to high. Okay, So that is the association that I want you to describe. Now that same association is true in this plot on the right. So go ahead and write those results out. All right, multiple regression assumptions. Now this for me is the most important part of the assignment, because if you fit a model and you cannot assess the assumptions, then you do not know whether that model fits the data, and you cannot trust the results from that model. And the largest problem I see for statistics are people fitting models that are not appropriate or do not fit the data and then drawing conclusions from them. So I want to make sure that you do not fall into that pitfall. So let's see. Getting a little distracted by my son who just woke up. He's making noise in the hallway. All right, so fit the multiple regression. Start by assessing the model assumptions and interpreting what you learn from the first 6 plots. Okay, so everything except the added variable plots. If the assumptions are not met, then we should attempt to address those assumptions by transforming a variable and then try again. Now, of course, this would be terrible because we've done parts of the assignment above that would change when we transform variables. So let's hope that we get away with using the data as they are. So here's the linear model. We got the y variable, tilde, age as one of the x's, and bidders as the second x variable. And we plot the diagnostics using the lmdiagplots function. And I ask, so I've got a whole bunch of plots that can come out of here, but simple AV gives sort of a simple 6-pack of plots plus the added variable plots. And I think we'll probably end up using this subset of plots most frequently. All right, so which plots are we looking at here? Let's look at these 6, and then maybe we'll say one additional word about this 7th plot. And then below that are the added variable plots for the next question. All right, so if I scroll down a little bit more, from the diagnostic plots above, this is where you'll fill in your answer. So let's scroll up. Now, I wouldn't necessarily, I've sort of sorted these in the order that I look at them. So I think it makes sense to just go from left to right through these plots. The first is the QQ plot that asks whether, oh, you know what? Oh, that's funny. All right, so sorry, I'm looking at something else. So the first plot asks whether the residuals are normally distributed. That's one of the model assumptions. And if the points sort of follow this center blue line, and there aren't too many of them outside these dashed lines, then generally speaking, I would say that the data or the residuals follow a normal distribution. You do see some systematic deviation from this. There's sort of deviates to the left of the line on the left tail and deviates to the right line in the right tail. So there's a little bit of evidence there for kurtosis. This is actually low kurtosis, what's called platykurtotic, that the residuals actually don't have tails that are as long as the normal distribution. They're sort of truncated a bit. That's just, in terms of a deviation from normality, this is a good deviation to have. We don't have outliers, really. And outliers can be very influential, and so we're not going to have points like that. So this works out pretty good. Cook's distance. There's a rule of thumb about Cook's distance in terms of, what are extreme influential points. And I've put that rule of thumb as a dotted line here. The way that I teach this and the way that I've learned it from others before me is that typically you're looking for there not to be like 1 or 2 points that are really high compared to the rest. And in this case, we always have sort of a low background set of points down low, and you'll have some that are higher. And in this case, none of these stand out that much more than the rest. So I do not feel that concerned about influential points in this data set so far from what I've seen from these two plots. In the third plot, we're looking at the relationship between leverage on the x-axis and Cook's distance, which has the same axis as the second plot. Now, leverage is a measure of how much a point is an outlier in the x direction. So in terms of the age and bidders variables, which observations are outliers? Now, if I scroll up a bit to this plot, age versus bidders, this one here, we don't really see points that are fantastic outliers. They're all sort of clumped together. You know, this point down here in the bottom right is an outlier because it is the most extreme age, it's the greatest age, and the most extreme bidders in terms of the lowest number of bidders. So it's the oldest clock had the fewest bidders. So any points in the corners you're going to see are going to be relatively extreme based on this plot, but we don't really have outlying points here. You know, an outlying point would be something like you've got a clump of points, say in the bottom left, and then up in the top right you've got a point out there. That would be clearly a big outlier in the x direction. It would be high leverage. These points are very well behaved, so we don't really see any points with big leverage relative to all the other points. What this plot with leverage versus Cook's distance says is it helps us understand why are points having influence. Right? Influence and Cook's distance, those go together. So if you have high Cook's distance, you have high influence on the regression model. And it turns out that the 2 points that have the highest influence with Cook's distance are also those points that have the highest leverage. So it's because they are unusual points in the x direction that give them more influence in the for the model. They have the largest change on the beta coefficients when those points are included in the data and the models fit. Anyway, these are not very extreme relative to the rest. I'm not concerned about these at all. But that would be my, what would I write down for the solution? I would say, leverage are the points. Leverage is a measure of how much points are outliers in the x direction for your predictors. And the 2 points that have the highest leverage also have the highest influence as measured by Cook's distance. However, these are not extreme for either leverage or Cook's distance relative to the whole data set. Therefore, there's no concern about model assumption violation. The next three are all about looking at residuals on the y-axis. We're looking at the fitted values here, which says that the fitted value is the predicted y value, and the residual is the distance in the y direction from the regression line. And even though I see this sort of V shape for this red line, without that there, I don't see a strong structure of these data points, of those residuals. The types of features we're looking for are like curvature, like a U shape or an upside down U. Another thing is heteroscedasticity, which just means a difference in variance. So, for example, if we had very little variance on the left-hand side and it sort of became more and more variable as we go to the right, then there would be a suggestion of heteroscedasticity. That non-constant variance is an issue because the regression model assumption is that all of our residuals follow the same normal distribution with mean 0 and a common variance, sigma squared. So I don't really see much of an issue here. Same thing with residuals versus age. This is basically flat. There's no structure here. Now for bidders, my eye is a bit deceived, and I sort of see this U shape, upside down U shape. But I think that relationship is not very strong, and I sort of agree with this red line that's just horizontal. So all these residuals look totally beautiful to me. I'm very happy. The last plot here in the bottom left, sort of an extra plot number 7, is the Box-Cox plot. It tells you what transformation should you make to the y variable, which power transformation should you make, in order to make the residuals most normally distributed. And the number 1 here has a sort of an orange or yellow color. That's sort of the ideal position. It means no transformation is needed. And here the center says that 0 is the transformation that you should make. So we should take y and raise it to the 0 power. That's a special case, of course. Any number raised to the 0 power is equal to 1. So in the limit for the Box-Cox transformation, the value 0 is actually the logarithm. And the dashed lines on the left and the right give you sort of a confidence interval about that transformation. Now, so there's some suggestion here that, in fact, 1 is outside of that confidence interval. So it seems like we should transform the y variable. However, when we've looked up here at the QQ plot, even though there's some evidence here that the points don't follow exactly a normal distribution on the solid diagonal line, they're all within these dashed lines, and they are quite well behaved. So I'm using my judgment. I would say that this may be a good suggestion, and if I was doing this for writing a research paper or something, I would certainly try this transformation and see how things change. But I don't see really strong evidence to suggest that we should follow this course of action. So I'm going to skip it. So those are all the comments I would make here. For the next part, added variable plots, use the partial regression residual plots, right? So the added variable plots to check for the need for transformations. If linearity is not supported, address and restart at the beginning. So these plots, I think I discussed them in detail in the lecture videos, but effectively we're asking for the relationship in the data after adjusting for all the other variables. So this x-axis here, we're asking these are the residuals. That's why 0 is in the middle. These are the residuals of regressing age versus all the other variables. And that doesn't include price, right? So we've got price and we've got age and we've got this others category. In this case, others in this plot on the left is the bidders variable. So we regress age versus bidders and we get the residuals. Now, what do those residuals represent? They represent the information in age that wasn't explained by bidders. So it's the additional information in age. And over here we've got price, the residuals of price after you regress it on bidders. And so this is what information there is in price after adjusting for bidders. So we've got sort of age that wasn't explained by bidders and price that wasn't explained by bidders. How is age and price still related after we adjust for bidders? And what we see is a nice positive relationship here. So turns out that even after we adjust for bidders, there's still a relationship between age and price. So age is an important variable. Secondly, the relationship is linear. There isn't curvature here. It can be the case, let me scroll up for a moment to this plot here, right? When we just plotted price versus age, this seems like just a straight line in terms of the the relation, not the straight line itself, but the pattern that we see in the points. It can be the case that on a marginal basis that age versus price by itself looks linear, but after you account for another variable like price, that you could get a curved relationship. And in fact, it would be that curved relationship that you'd want to include in the model. So this basically says that after you adjust for bidders, age and price are still related, and that relationship is linear. So age on a linear scale is the right variable to have in the model. let's look at the other way. So now in this plot, the second one on the right, others is the variable age. So we get the information of bidders after adjusting for age. That's the residuals. And we get the residuals of price after adjusting for age. And we ask, what is after you adjust for age, what is the relationship between bidders and price? And that relationship is positive, and it looks linear. Now, my eye sort of makes me think that there's a slight downward curve to this. If there is, it's not very strong. And we may not really have enough evidence to, say, include a bidders squared term or the log of bidders, or a square root of bidders, something like that. Anyway, those are just some thoughts. I think with only 32 observations and this pattern, I think just bidders by itself is just fine. Anyway, so this, like I said, this data is like perfect. It's a very easy example. It's very, very clean. Everything works out. But those are the interpretations for those added variable plots down here. Linearity is supported, no transformation needed. All right, multiple regression hypothesis tests. We've got our linear model here, and we look at the summary of that. The output from the summary command tells us how this, what the model was that was fit and the data set that created the output. It gives us a 5-number summary of the residuals. Basically, we're looking for symmetry here. I actually rarely look at this output because I'm looking at the plots instead, but the median should be somewhere close to 0, and the first and third quartile should be about the same, but negative, positive, and the min-max should be roughly the same. Then we've got the intercept. So this is sort of interesting, right? We have a negative intercept, but of course, well, do I ask you to interpret it? Yeah, I guess you should, down here. So we have 3 estimates. We have the intercept, we have age, and we have bidders. So let's start with age and bidders, and we'll come to the intercept last. So multiple regression. All right, I don't actually ask you to do the hypothesis test, I think. Let me just double check up here. Oh no, state the hypothesis test and conclusion for each regression coefficient. Oh, I see. And then the next question is to interpret the coefficients. All right, so let's do the hypothesis test first under this solution. So for age, we have got a p-value that is less than 0.05. So the hypothesis here, the null hypothesis, is that the coefficient for age equals 0. The alternative hypothesis is that the coefficient of age does not equal 0. We have a p-value that's less than 0.05. Therefore, we reject the null hypothesis in favor of the alternative hypothesis, concluding that the coefficient for age is different from 0. So if you basically type exactly what I said, that would be a fine answer. You might include a few more details, like that the t statistic was 14.11, and the p-value is, whatever this number is, 1.6 times 10 to the negative 14, and compare that number to 0.05 and make the conclusion. Okay, similarly, you get the same answer for bidders, and so write out a similar statement for bidders. We don't really care about doing a hypothesis test for the intercept. We only really care whether the relationship holds. The regression model, there's support for including age and bidders in the model. All right, so interpret the coefficients. Let's just focus on age and bidders and not worry about the intercept. The intercept's not really interpretable because there aren't any clocks where the age was 0 and there were no bidders. So that would be the interpretation of the intercept. It's the expected response, or the expected price, when all of your x variables equal 0. So for a new clock with no one's bidding on it, it's negative $1,000. That doesn't make any sense. We don't have any data. This is extrapolation down in that region. Okay, multiple regression interpret coefficients. So that's these numbers here. So for every unit, so I would say something like the coefficient of age is estimated to be 12.7. Thus, we expect for every unit increase in age, we expect the response variable price to increase by 12.7, holding all other variables constant, which means if you hold the number of bidders constant. Okay. Similarly, I'll probably state it in a slightly different way this time. So the estimate for bidders is 85.8. Therefore, we expect an increase. Maybe I'll say it this way. Holding all other variables constant, meaning holding age constant, we expect an increase of 85.8 pounds sterling in price for every unit increase in bidders. So for every additional bidder. And that's those are good interpretations for those two coefficients. So sort of write that in your own words, whatever sort of language you feel is easiest to use. And then finally, the multiple regression R-squared value. All right, so that is this number here. So I would say, so the regression model explains 89.27% of the variability in price, that's the response variable, over and above a model that would only have the mean of price. Yeah, so this term sort of compares two models. It compares the model where you don't have these regression terms over here, you just have a number 1, basically, or a beta naught. You're just estimating the intercept. So if you do that, then you're just estimating the mean for price. So that's a horizontal line, right? If we scroll up here to any of these plots, you're looking at the average price. Maybe it's like, I don't know, for $1,500 or something, and you're drawing a horizontal line. So you end up with large residuals if you just plot a horizontal line around $1,500. Same thing over here, right? So if instead you fit this two-dimensional surface, then you get much smaller residuals. And it's that relationship of the sum of squared errors and the proportion of sum of squared explained by the model that gives you this multiple R squared. So we can basically do like 90% better in a way. We can explain 90% of the variability of price by using this model. This is a very high R squared. In practice, you're very lucky to see data that a model that fits data so well. In biology, you're thrilled to get like 0.2 or 0.15 on the R squared because many biological systems are just very, very noisy. All right, in the last part here, I've got a summary. So summarize your findings in one sentence, right? This is what you'd tell your advisor after you've spent 3 hours on this, on analyzing this data. Your advisor asks, what did you learn? And you say, well, using all the data without transforming any of the variables, there were significant positive linear relationships between price and both age and the number of bidders. And that explained about 90% of the variability in price. Right? So in a way, I just sort of started from the beginning and sort of scrolled down in terms of the ideas that were important. So I'll say that one more time. So we didn't transform the data. So I would say, using all the data values without transformation, there is a significant positive relationship, and it's linear, between both age and the number of bidders. And that evidence came from these plots. It came after we we assess the model assumptions. We can probably include a comment in there about model assumptions as well, though it's sort of assumed that the model assumptions are met, but let's not make that assumption. So we're significant positive linear relationship. We also saw that in the added variable plots. So after you adjust for the other variables in the model, we still have these nice positive linear relationships between each variable and the response variable. And we see that here as well, that these estimates are positive and they're significant. So that's the evidence that contributes to that statement. Explaining nearly 90% of the variability in price. That's the multiple R squared. And if you wanted to also say that all model assumptions are reasonably satisfied, or that no model assumptions were violated, you can add that statement in your summary as well. All right, that covers the whole assignment. Just for fun, I want to show you this code right here. So I will jump down to the bottom and let's run this. And I'll make sure I bring this image down to my recording window. So this is what we're actually fitting. Now all the plots we saw so far were just like two-dimensional plots. But of course we have three variables. And so this is what we're fitting. We've got price on the vertical axis. We've got bidders on this blue axis to the right. And we've got age on the pink axis moving away from us. Okay? So we can look at this in sort of cross sections. Let's start sort of here. Here we're looking at it sort of sideways with price on the vertical and age on going off to the right. And these points, are sort of heading up and to the right. So that's the positive relationship with age. And if we rotate this way, okay, now we've got price on the vertical axis and bidders on the x-axis, and that relationship is sort of also increasing. What's even nicer is sort of looking at it in this way, where as both age and bidders increase, price increases. There are some other features that you can see in a three-dimensional plot that you can't see with a two-dimensional plot. In particular, this is a nice view. Okay, so we're way up in the positive space, and we're looking down at the origin. And one thing I see here is a pattern of the residuals that I could not see before. Right? There's a bit of a curvature here, that when there's high bidders, well, it's a little bit tricky to make that interpretation. But anyway, there is a pattern to these residuals that's sort of negative over here, positive in the middle, and negative over here. So in that direction, it seems that there is a pattern in the residuals, and we may want to consider a transformation to capture that. Now, we don't have a very large data set, and I feel very comfortable with the conclusions that we've drawn in the previous analysis. You can also sort of see it here that the points on top are in the middle, and the points that are on the bottom are on the sides. Let's sort of look up at it this way too, from the bottom up. But if this was like a really consequential analysis, and especially if we had more data points and we saw a curvature like this, we might start to think about adding, say, age squared and bidders squared to incorporate some curvature into the regression surface. But that's everything for this assignment. I hope this introduction to the assignment has been very helpful for you, and I'll see you on the next assignment.